So as you know, we have been doing our lesson planning in 3 modes: observe and explore, define and prove, apply and evaluate. The aim of observe and explore is to do either a video sharing or a problem or a real world problem or a puzzle, so that you come to the concept that is going to be taught in your class at that time. So observe and explore is observe, explore and come to the concept so that students understand that this is what is important and is going to be done. Second stage is define and prove, and that stage you do your actual teaching of curriculum, namely from the chapters, theorems, proofs, definitions and so on. So that is the chunk of the time is spent by you in doing this define and prove. And third part is apply and evaluate, where we will we have been telling you how to give some kind of applications of the topic that you have taught, and try to evaluate by some non-routine problems, so that you can judge whether the students have really understood the importance of the topic under consideration. So let us begin with the for the topic today, observe and explore. So let us look at a video. Yes, good. So motivated by this excited video, let us pose a problem. And the problem is the following. Two ships are 6 units apart. It could be 6 miles or 600 miles or anything. It doesn't matter. Are 6 units apart and both are moving along a straight path joining them. So there are 2 ships and they are moving along a straight path joining them. The ship D is moving towards at a speed that is twice the speed of the ship E. So there are 2 ships, one is called D, the other is called E. And they are moving along the same straight line. D is moving at a speed that is twice the speed of E. So here is the picture, and we want to find the point where they will meet. Here is D, here is E. They are moving along this straight line, and we want to know where they will meet. So I would urge you to think about this problem for 2 minutes. This is not a very difficult problem, and this is a digital session going on online. So I can't see what you are writing in your notebook or ask you to show it, but try to write in the chat session what will be the location of the point P where they will meet. So I give you 2 minutes to have a look at it and add in your chat session the answer, whatever you think. The point P is located at what? Keep in mind, there are 6 units apart and D is moving twice the speed that of E. So we want to know what is the point where they will meet. So write your answer in the chat session, whatever you think. So take 2 minutes to work out and write your answer in the chat session. So that will tell us that you are thinking along with us. And so I'm giving you 2 minutes. I'm waiting for some people to enter in the chat session. Yes, somebody, Alankar Anand has entered. Alankar has entered his answer. Good. Ramesh Chavan also has answered. And that's good. We are thinking about it. So please try to, so that we can make it more interactive. Yes, most of you are getting the right answer. The number of units, how far it is from D to the point E, right? Yes, most of you have gotten the answer. So let me go ahead. Others need not enter now. They can wait for the next. You see, in this, as the picture says, as the picture is showing, that D is moving towards E and E is moving towards D, right? So that is what it looks like. So that is the case 1, that ship D. So that is the assumption that is already made, that the ship D is moving towards E. So D is moving towards the right side, towards E, and E is moving towards left side, towards D. And we want to find out the point of intersection. And most of you have guessed the answer correctly. So let me show you how this can be done in a, it's a simple problem, analytically can be done, but how we can animate such kind of things in GeoGebra, right? So this is the point D, and this is a shape D, and this is a shape E, okay? So let us skip the meeting point, and let us skip this answer also, okay? So this D is going to move towards E, and E is going to move towards D at twice the speed. So let me animate and see. So here is a nice thing in GeoGebra you can do. D is moving at twice the speed, and so this is where they meet, okay? Of course, it can go on, right? So there is a backward journey, you can think looping, that D is moving towards E, right? So what is the meeting point? This is the meeting point. We will see it again. That D is moving and E is twice the speed, so they will meet at that point. And the distance, as most of you have guessed, is 4 units from D. So I'm just bringing in GeoGebra to make things slightly more interesting from the student's point of view. And you can do this simple animation in GeoGebra. It's quite simple. If you already know GeoGebra, that's good. If not, it is a motivation for you to learn GeoGebra. That point P, if you know the ratio and proportions and internal division in some ratio, 2:1, so you know what is that point P, where they should meet, right? But here in this case, we made an assumption that D is moving towards E and E is moving towards D, right? Let us change the scenario a bit, namely that ship D on the left side of skin is moving towards E and E is moving away. So the D is moving towards E, it's coming on this side, and E is moving away from D, it's going on the opposite direction. So, but speed of D is twice the speed of E. So eventually D will take over E, even if it is moving in the opposite direction. So try to put your answer, what could be the point P, what could be the location of the point P in this case. So try to compute and put your answer in the chat box. So I'm giving you 2 minutes to check and put your answer in the chat box. As soon as 3 people get the answer, we'll move ahead. So to check what is the right answer for this, let us, yes, good. I think this is a nice and simple problem. You can take it as a problem in physics if you like somebody moving at some speed and so on, but there is mathematics involved. So a lot of people have put in the right answers. Some people have not put the right answer. So let us see what could be a possible way of looking at it. GeoGebra. So the problem we are looking at is D is moving towards E and E is moving away from D. So the point P where they will meet, and we were trying to see it in the GeoGebra.
Yes, you can proceed.
Okay. So we are looking at the GeoGebra animation for this problem. So D is moving towards E, E is moving away from D, and so at some time point D will meet E, and that is the point P where they meet. So let us, that is the point P, okay. And the distance is 12 from the starting point. Starting point to taken is D, okay. So again, this is a simple animation in GeoGebra, and mathematically if you want to analyze this problem, then it is the point P which divides DE externally in the ratio of their speeds. So that is how you will, the ratio is 2. So externally this should be, this distance is 6. So it should be 6 times 2, that is 12, right? So this brings in ratio and proportions topic of that we teach in the secondary level. It also brings in the external division of a point and the internal division of a point. So this was probably case 2. Nobody thought about it because when you said moving, it looked like where D and E will meet. So automatically one took it as D is moving towards E and E is moving towards D. That is the first case. So second case, normally sometimes there is another lesson to be learned, that whenever a problem is given, look for all possible cases that can arise before solving it. So here is a variation of this problem which was posed by Apollonius. You must have heard about the geometer of the Greek period, Apollonius of Praga. He was from Praga, a place, and he posted the following problem. Now the ships are not moving along the same line. So what you are given is, given a ship A is moving with constant direction and speed with a speed V. So this A is moving along this direction, okay, along this direction, the red one, okay, and the ship B is moving towards P with some constant speed, that is capital V, okay. So this is the motion of 2 ships, but they're moving along the same line, same direction is fixed, and their speed is also fixed. So and let us assume that they will meet at a point P, okay. So obvious things are that if this speed is, somehow the speeds coincide in such a way that they meet at the point P. So what is the problem? The problem is what is the locus of the point P. We want to find out the possible points P in the plane where the two ships will meet. Right? If you want to make it more interesting, A is a pirate ship, B is a Costa Guard, and they are trying to catch. But these are the lines to make it mathematical. We have fixed the directions of the two are fixed. The speeds are capital V and small v, and we want to know where they will meet. So find out the locus of the point P. So again, I give you 2 minutes to think and write your answer in the chat box. So I'll try to keep an eye on the chat box and see how many are able to write their answers. At least if I get 5 answers, that will mean that people are trying. So what is the locus of the point P? Now, keep in mind the question, read the question clearly. What is the locus of the point P? So that should give you a hint that unlike the now, so the hint is as follows. So A is moving along a straight line and B is moving along a straight line. Of course, the assumption is both start at the same time, right? It's not that A has already started and B is still waiting for something to happen. A and B start at the same time and they meet at P. Of course, they are moving along different lines and with the speed capital V and small v. So how much time, and so assuming that they meet at the point P. So how much time A will take to reach P? Can we calculate that? Of course, we know the speed, distance is AP, okay. Can we calculate the time taken by the ship B to reach P? Yes, the distance traveled is BP and the time taken is T. And the speed is given capital V. So what will be the time taken? So physics, the time taken is the distance divided by the speed. But A and B start at the same time and they meet at a point P at the same time, whatever time is. That means the time taken by A and B to reach B, A to reach P, B to reach P is same. So the speed by the distance AP is equal to speed by the distance BP. That gives us a relation, right? So that gives us a relation between the speeds. So let us look at that. So let us call that ratio because V is fixed, capital V is fixed, small v is fixed. So that means capital V by small v is a constant, right? Because these are fixed. So that constant, let us call it as R. So what is required now? The problem can be solved now by finding all points which can be simultaneously reached by both the ships. The distance PA by PB is equal to R. And we know the distance formula, right? So here is where coordinate geometry comes into picture to solve this problem. Let us go to the plane, okay? And let us assume this is a situation. Let us say A and B are on the x-axis and the point P where they meet is somewhere in the plane, right? We can have the coordinates and let P have the coordinate x, y. So we had come to the stage of saying that because the time taken by both the ships A and B to reach P is same, so physics tells us that that time PA by PB, the distance is V by small v. That ratio should be equal to R, and that is a constant. So this is what we know from the given data. Now to find out the locus of the point P, let us go to coordinate geometry and let us assume the point P has got coordinates x and y. So x and y are the coordinates of P, which we don't know. M is m comma 0 we can say the coordinates of the point A, P comma 0 is the coordinates of the point B. Okay. So they are on x-axis somewhere, let us assume that. So that we can find out now the distance AP, and we can find out the distance BP from coordinate geometry. So xy, m0, the distance will be x minus m whole square plus y minus 0 whole square. That is the distance. That divided by this distance using the coordinate geometry distance formula, x minus p plus whole square plus y minus 0 whole square. That ratio is equal to a constant. And if we put that, so that is what we get. So PA by PB is R, which is same as x minus p square plus y square. That is the distance, this distance. And this now, so this part that R is equal to this part can be now simplified by squaring its own, and you get the equation that x minus r square m minus p divided by this plus y square is equal to 0. Plus y square is equal to this constant. So that says it is a quadratic implicit equation in x and y of degree 2. So it is something like x minus a whole square plus y minus b whole square is equal to some t square. So that is the equation of the circle. So mathematically what we are saying is that the point where they meet, given that they always move along a line, okay, and the speeds are constant, s and capital V. Here I probably have changed my notation. This is the speed of other is speed b. So that ratio is a constant that we already know, that is equal to r. So mathematically it says that the locus of the point P where they will meet is a circle. And this problem was motivated by the question that Apollonius had asked. So let me go back and show you a GeoGebra version of the same, finding this locus. Okay, PA by PB is equal to R. So here is, okay. So let us, now what I'm going to do, I'm going to animate the point P to see where the possibilities are, given that AP is equal to R times this thing, where ratio R is 2.2. Why it is not visible here? The number R, show the label, object properties. Let me just change that, basic ratio R, caption, and value. Okay. Yeah. Now, so this is that ratio R, right? That was depending on the speeds, that was a constant. If the ratio is 2.2, say, then what is going to be the locus? So here is the locus of the, you can see how the point P is moving so that the ratio remains the same constant. So AP by, okay, that is the ratio. You can see it here. Okay. And so now you can try to make a guess that what should be the locus. And if you want slightly more dramatic thing, let me put a trace on, which is possible. As the point P moves, it will leave a trace on the plane. So this is what the locus looks like. So the locus is a circle. Of course, the center is not B. The center is somewhere else. Okay. And the radius is also not equal to R, this ratio. Ratio is something else. Okay. So if I change this ratio, it will be a different circle. So if I change this, proposed by Apollonius, and he, by his problem and his solution, he defined the circle as the set of points in a plane that have a specified ratio of distances of two fixed points. And we saw it in GeoGebra also. I hope all were able to see that. animation in GeoGebra. I don't know. Maybe I should repeat that, just in case some of you had missed that. So this was, I have 2 points A and B, which are fixed, and P is a point which is where they will meet depending on the speed. R is the ratio. Okay, so that ratio was not visible here, so I had enabled that. So basic, caption, and value. Yeah, so that was the ratio, and we animated this point P with a trace on, showing us what is the locus of this point P. So that motivates this kind of animation will tell students that there are objects, closed bounded figures, which are not rectilinear, and they are given the name as circle. Okay, so let me go over to the same. So having come mathematically and via GeoGebra to the concept of an object called a circle, right? So this is the equation that we saw. So let us look at define and prove. So basically, the idea is basic concepts which should lead to a circle, understand static and dynamic definition of a circle. Okay, and you see, what is the static and dynamic definition? The static definition is the distance of all the points. The standard definition that we give is the static definition, and dynamic definition is the one given by Apollonius, and various concepts called. And so all this goes into define and prove, which is the standard material in your textbooks. So, so we have already done this part. GeoGebra is an important aspect that can be used to illustrate many things. Okay, right. So here is one thing normally which we don't stress, or maybe the curriculum also does not stress, is geometry is one way of looking at things which are quite visible. Okay, but there is another way of looking at geometric objects, because after all geometry is being done in the plane. So look at geometric objects in the plane. We can use coordinate geometry very effectively, and that is more satisfying. That gives a computational way of verifying things in geometry. So I'm going to show some things, how these things are useful in doing computational aspects. Right. So here is, first of all, the plane R2, right, with what we call as x-axis and y-axis in coordinate geometry, is a set. So here is a set theory coming into picture also. It is a set denoted by R upper 2, saying it is 2 copies of R, where x coordinate x comma y, it is an ordered pair, x comma y, x comes from R, y comes from R. Both are real numbers. X is called the x coordinate, y is called the y coordinate of the point. Okay, P. So every point in the plane, we had seen in geometry, locating a point in the plane, every point in the plane can be associated with a ordered pair x comma y, and every ordered pair x comma y gives a point in the plane. So the plane, geometric object plane, mathematically in coordinate geometry is written this way. Okay. So what is a circle? A circle is the set of points. A circle is with center, say AB, O is the center, R is the radius. So if you take the definition of our textbook, it is all points at a constant distance. So XY, all points at a distance from AB, x minus a square plus y minus b square equal to R. So that is a coordinate way of telling what is a circle. Okay, so a circle is a subset of R2. That is another way of looking at circle. Okay, so it is, if written this way, then it automatically tells you it is a circle where the point AB, the fixed point from where we are taking the distance of the point XY, that is the center, okay, A comma B, and R is the radius. So that is bringing coordinate geometry, right? So the circle now partitions geometrically. If we look at it, the circle partitions the plane into 3 disjoint sets. Okay, so this is in geometry what we call as the circle, the red one. The pink is called the interior of the circle, and points outside in the plane which are outside this red circle are called is called the exterior. So a point is called exterior. If it is outside here the circle, inside, that is called interior. On the circle, that is a point on the circle, right? So this is a geometric description that looks quite obvious, that every circle should divide the plane into 3 disjoint parts, right? But mathematically, it's not an easy job to prove that every simple closed. So a circle is what is called a simple closed curve, and to prove that every simple closed curve will divide the plane into 2 parts, into 3 parts. One is the curve itself, and other is the interior, other is the exterior of the. It's not a very easy job. For example, I can't show you here because I'm on a desktop. Otherwise, I could have drawn. See, if I were just think of this mouse moving. So you are going like this, doing like this, doing like this, and without intersecting, come back to that same point. Okay. If you open it, that looks like a circle, closed figure, but it's very difficult otherwise to pinpoint what is the interior, what is the exterior of a circle, right? Okay. So let me not go much into it. It's a deep theorem by Jordan saying that every simple closed curve will divide the plane into 3 parts. That looks very geometrically very obvious to us. So we can, these 3 parts, we can write mathematically in coordinate geometry. The interior of the circle, all the points at a distance strictly less than r, all the points which are at a distance strictly less than r from AB, the circle where the distance is equal to r, and the exterior where the distance is bigger than r. This is a mathematical way of verifying whether a point is inside or outside a circle. Okay, interior or exterior or on the circle. A circle along with its interior is normally called a circular region. So circular region is the interior plus the circle itself, right? That is called a circular region. All right. So let us go ahead a bit. So recall, given a point in the plane, we could now doing a bit of define and prove. Some concepts I will just illustrate. Given a point, you can draw. We know that you can draw infinite number of lines passing through a point. Given 2 points, we can draw only 1 line through them. That is what geometry says. That is what one of the axioms of geometry says. Include an axiom that given 1 point, there is infinitely many lines passing through it. And given 2 points, there is actually 1 and only 1 line passing through those 2 points, a unique line. And given a point plane, now we ask a similar question about the circle. Given a point plane, how many circles can be drawn through it? Of course, we will say the answer is infinite because there are as many as we want, or you can say there are infinite number of circles that can be drawn through a point. Because a point, if it is on the circle, the center could be anywhere in the plane, and there are infinite possible centers, so that makes it infinite possible circles that you can draw. Here is something that you can do in GeoGebra for the sake of fun. So I think most of you have already done this kind of a thing. So this is a circle. This is the point A on the circle, and that is the radius. So I can, that is the circle. It has some center. I can animate what is the center. So it gives them many different possibilities, right? You can either this side or that side. So this is a kind of a fun but learning mathematics that you can draw many circles, right? Infinite number of. This is the point, there is a center. Or you can, in GeoGebra, you can take another point on the circle. So you can take a circle passing through another point, and that point can be animated. Okay. So this is, so the question was, given a point A, how many circles can pass through it? How many circles can be drawn? The answer is infinite. So next question obviously is, how many circles can be drawn through 2 points? Again, the answer is infinite, right? So here is the infinite. Okay, you can do it in GeoGebra again. You can take 2 points and take a possible circles of different radii passing through them. Okay, so one can do it in GeoGebra. Let me not go too much into GeoGebra. So next question that obviously comes is, one and only one circle can be drawn through 3 different points in a plane. So that is a theorem. The question is, how do you prove such a theorem mathematically? So here is something in triangles that should come to your mind, that if you want a circle passing through these 3 points form a triangle. And if you want a circle passing through the vertices of the triangle, you know what is to be done, right? There is the concept of, so here is what, look at the altitudes, where the altitudes to 3 different sides meet. That point is called normally the orthocenter. So if this will be the center of the circle through which that will pass through these 3 points, and one can easily prove mathematically that you must have already proved in the section on triangles that O is at equidistance from A, B, and C. Now, so this will only prove that you can draw one circle passing through these 3 points, but only one circle that needs to be established, and I will leave that for you to think and say something about it. Analyze. What we have shown is, if A, B, and C are 3 points in the plane, then we can draw a circle passing through them. They lie on a circle. But there is only one circle. Why? What is the reason for that? Try to justify that, and use your WhatsApp group to put an answer to this question. So this is a question which I am leaving it as unanswered for the time being. For those of you who are keen, think about it and put your answer to the question, why there is a unique circle passing through 3 points in the plane. Okay. Right. So let us go ahead on analyzing something about circle. So here is another question that you can ask. Can you go beyond? So given 4 points in a plane, so that no 3 of them are collinear, does there exist a circle passing through all? That is a question you can ask, right? Given 3 points, which are not, given 4 points in the plane which are not collinear, does there exist a circle passing through them all? Is it possible? So these are the 4 points, A, B, C, and D. Now no 3 of them are collinear, because if 3 are collinear, those 3 will not lie on a circle, right? Okay. So of course, A, B, and C, you can have a circle passing through them, right? Given any 3 of them, you can have a circle passing through them. So how many in all are possible? That is another question you can ask. So how many? So there are two questions. One is given 4 points which are not collinear, does there exist a circle passing through all? Can we have at least one circle passing through all the 4 points? And will there be a unique point? That is another question you can ask. Will there be a unique circle passing through them? 4 points. Can we have one, and will that be unique? How many different circles can be drawn if the circle passes through exactly 3 given points? So that is a question of now permutation and combinations. So you can solve both of them actually very nicely in GeoGebra. So let us look at the first one. Given 4 points in a plane. So these 4 points that are in a plane, if the circle is to pass through them, they should be concyclic. All they are concyclic points, and you know a property of concyclic quadrilateral that the sum of the opposite angles should be 180 degrees, right? So that gives a way of saying that yes, this will be possible to do that once these points have these property. They are so they opposite angles. So there is a possibility of passing through that. Okay, and this you can move around these points. I hope yes, you can move around. Okay. See, there are many. So points could be anywhere, but the circle is the same. Okay, so you can do that. And second question is that how many circles you can pass given 4 points. How many circles are there with 3 points at a time? So this is a circle passing through A, B, and C. This is a circle passing through A, B, and D. This is a circle passing through. So given 3 points, there will be a unique circle. So that is okay. So there is only one. Okay. So this is B, C, and D. So that tells you there are 4 circles. So that they pass through 3 given points out of those 4. Okay. This is a nice questions to analyze about. Students will get familiar with circles. Students can analyze them in GeoGebra and get in. Their curiosity will be aroused and they can do it. Now here is the next set of analysis we want to do geometrically. If you are given a circle and you are given a line, at how many points a line can intersect a circle? One possibility, of course, is it lies outside. Completely, it does not intersect. Other possibility is like this, it intersects at 1 point, and the other is it cuts the circle at 2 points. Right? The question is, can you prove this? Geometrically, it looks very obvious that yes, given a circle, once you're outside, this line will never, so like this line L, will never cut it, right? Or if I go on bringing it closer, probably it will look like the line M, which intersects it at the point G, okay? At only 1 point, and then possibly at 2 points, okay? In GeoGebra, it's very easy to check, okay? But can you prove such a thing mathematically? Because we know the equation of the line, we know the equation of the plane, equation of the circle, given center, given radius, we know it. So can you prove it mathematically? That is the question. One way of doing that I think one way of doing that is the following. I'll just say it orally. The equation of a line is a relation between x and y coordinates. So it will be, you can, one way of stating this is a line is y equal to mx plus c, where m is the slope and c is the intercept on the y-axis, right? So that is y equal to mx plus c. There are 2 coordinates, x and y, 2 variables related linearly, right? And for a circle, the equation is x minus a square plus y minus b square equal to r square if AB is the center and r is the radius. Now, if a point has to lie on the line and on the circle both, then that point, if we call it as x, say x0, y0, then it must satisfy this equation of the line as well as satisfy equation of the circle. Now, from one equation, say equation of the line, you can find, say, y0 in terms of x0 and put that value in the equation of the circle. That will give a second degree equation in the variable, other variable, that is x0. So you get a quadratic in x0, and that quadratic in x0, we know now quadratic equations, solutions of quadratic equations come into picture, that a quadratic equation may not have a solution. If it does not have a solution, this line will not intersect. It may have two coincidental solutions. Then it will be this situation, line M, and there could be two different real numbers which are solutions that will correspond to the line N. So one can prove it mathematically by solving equations of the line and the circle, looking at the coordinate geometry equations and solve them for the two variables. So one can prove them mathematically. That is not a big thing, and I would suggest that you try to say it at least in your class, that why such a thing, why this geometric fact follows surely from analytic fact. Okay, so line. So mathematically, you can say, as a set, line is a set of points with ax plus by plus c. Or there is a slight issue here. I am using the same a and b for the line and say a and b for the center. That is not really a good idea. One should change that. These two, we should have different ones. Okay, so line as a set of points is inside the outside of the circle, and the outside of the circle is this. Similarly, line will be another way we can say is that these are two disjoint sets when they don't intersect, right? So in set theory also you can write a line is outside when the two sets are disjoint. So that is what I'm saying is the following, that this line can be represented as a set of points, the circle can be represented as a set of points. So if this line as a set of points is disjoint from the set of points as a circle as a set of points, then this line will not intersect and so on. So you can go to set theory and write this in set theory also. It's nice to bring in various topics and show how they are used in one and another. Okay. Now, coordinate geometry is not something different from, is not to be done only for itself. It is used in various other branches, other parts of mathematics, itself, algebra, geometry, and so on. So, right. So this is what probably I was saying, that if they intersect at a point which is common, that means if the point satisfies both the equations, that means if this is the equation of the line, this is the equation of the circle. When this, we put this in this equation, you will get a quadratic, and if that quadratic has coincidental roots, that will imply that there is only one point of tangency, that is x0, y0, and that point is called the point of tangency, and the line is called a tangent. So that is a definition, mathematical way of defining a tangent. Geometric way of defining a tangent is this is a line which touches the circle only at one point, right? Touching at one point does not really very good ideas to make it mathematical. This is a mathematical way of saying that a point, if there is a common point of intersection, only one point of intersection, that means it satisfies this equation, right? It satisfies this equation and the equation of the line also. So then that is a point called the point of tangency, and the line is called a tangent line. So here we'll call G as a point of tangency, and G will be called as the tangent, right? So one can, when the line intersects the 2 points, right, then we say it is a secant line. So that line is called a secant line. Okay. So again, one should say there will be 2 equations in x1, y1 and x2, y2. And I have written by mistake only 1 equation. So like point will be, the 2 points will be on the line and plus the 2 points will be on the circle. So there will be another 2 equations for that. All right. So that is called a secant line. I'm just trying to show you that those geometric definitions of a tangent and secant, how they can be made mathematical, more precise. So you can define the notion of a congruent circle. 2 circles are said to be congruent. Notion of congruency, 2 objects, 2 shapes in 2 objects in the plane, as normally we call them congruent if they're the same shape and size. So 2 circles will be congruent. Once if we put one on top of another, that means if their centers coincide, then their radius also are equal. So they are called concentric circles. So this is a way of generating concentric circles. You can do it in GeoGebra very easily. You can have a slider R for the radius. Those who know GeoGebra, I'm just giving an input. You can have a slider R constructed and you can draw a circle with a center, right? So with the radius as R. So if you want me to do it, just for the sake of those who don't know GeoGebra at all, let me do one simple GeoGebra construction. So this is basically what I said. So this is circles, right? How did I do it? So let me show you how to make it. So let me new, don't save. So this is when you click on GeoGebra, this is what you get. So let us create a point which is a center. So let us create a point. So select point and create a point. That point is called K. So that is going to be the center of my circle. I want to choose a radius which is variable, which I want to move around. So let us call this as, so this is a slider thing. I select slider and click, I get a slider R. So that is a slider R, and let us say it is a number. It is going to be, you can fix value of R changes from what to what. It's too big a number, probably one can, it doesn't matter actually. So let us say it is 10. And the increment is 1 unit, so it will change. N will be equal to 1, 2, 3, 4, and so on. So when I click, I get a slider R, a slider N here. So let me create, now I want to create a circle. So I go to the circle tool. So in the circle, I want the radius to be equal to N. So I choose this part of the tool, a circle with a given center and a radius. So this is my center, and it asks me what is the radius. And radius is this N, so I'll enter N. Okay. So center is A, radius is N. So click OK. It creates a circle with that as the center. So if you want, I can change the color of this a bit so that it looks nice, and I can change the color to say the red. Style slightly bigger is okay. That is fine. So that is a circle. So that is a circle D. Is given a name to the circle. If I don't want the name, I can just click here and the name is gone. Okay. So now I can move the slider. If I move, see, this is a circle with center as A and radius is, this is C, circle is C. So here is a circle with center as a point, which was the point 4 point coordinates. These are center coordinates, and radius is equal to R square, that is 4. Okay. So x minus A square plus y minus B square equal to R square. So it gives you different circles. Right? So, okay. So let me not say wait. I just wanted to show for the sake of those who don't know GeoGebra at all, that it's not very difficult to do this kind of application. Okay. It will make students understand that for a circle, a center is required, a radius is required. You can move the center, if you can move the radius to change. Okay. So these are all circles. So let us, they are all concentric circles. Circles with different centers and different radii can have at the most 2 points of intersection. Again, why that is the case, that can be proved mathematically. That how many common points of intersection could be there if x0, y0 is a point of intersection, then it should satisfy equations of both the circles, and then we can try to solve those equations, simultaneous equations, and try to find out the values. Right? You will not be solving linear equations, 2 equations and 2 variables. Right? You will be solving non-linear quadratic equations. Circles which have no, that will again go to quadratics, trying to find solutions of quadratic equations. So possibilities are no solution, so no intersection of circles, or 2 or only 1 point of intersection, then that gives you the touching circles. So again, proving these facts mathematically requires you to go back to coordinate geometry, equations of 2 circles, and try to find out a common value that satisfies both the equations. Right. So intersecting circles and touching circles. There are many topics in circles of interest. So I will not go through all of them because they are all standard. What is a chord? What is a diameter? Right? And various facts. So you can, when we circulate the video of this, you can slowly pause and read what I'm saying. So various ways of expressing the circle. So angles subtended by a chord and so on. Various possibilities arise. The point P is inside, the point P is outside. And the interesting thing is all of these things can be very well illustrated using GeoGebra. Geometry is very easy to illustrate with GeoGebra. So that is the fact I'm trying to bring in. Wherever you see this symbol in my presentation, that means there is a GeoGebra applet. I can click and open that. So I will not do that. Chords, and there are theorems about chords and angles, right? So how the chord bisects and so on. So let me not go into all these things. These are all theory from your curriculum. So I'm trying to only show you in this presentation something which is extra, which is not in the define and prove part of your curriculum. So these are all standard things. Let us come to something, apply and evaluate. Here is something very interesting I discovered, how circles are useful or how circles are used. In this video, there is something called sacred geometry. But have a look at it from the point of view of how geometry and circle are getting illustrated in creating various things. I'm just pausing this video for a time being to say that I downloaded one of the videos from YouTube and I'm showing you that. But it will be interesting to do this animation in GeoGebra. So all those of you who are experts in GeoGebra already, and if they are part of you watching this, try to create all these animations using GeoGebra. Right? It's not difficult to do it. It requires a bit of labor. You'll have to do translations, you'll have to do rotations, you have to do magnifications, and it will help you to learn many things in mathematics, in geometry. So please, those who are experts in GeoGebra, do this in GeoGebra with animation, and please share your applet with me. That will be very nice. That will be your contribution to my collection of applets also. Of course, it will remain under your name. Okay, and GeoGebra is open source. Many people are putting many fantastic things on the web for everybody to use. So I urge you to create this in GeoGebra and share with all of us, not only with me, with all teachers. Here is another animation can be done in GeoGebra. There are some these are not circular objects, they are actually spherical, more or less. But these are sort of circular, spherical objects. They look circular because we look only two-dimensional of them. So students will like it. And now here is something which is a bit interesting from the point of view of how man discovered a circle and what is the use of circle or circular objects. It's a short animation, discovery of circular objects and how it has played an important part in our life. So please watch. So this was a short kind of how circles are around us and how they help us in doing many things. So it is just to catch attention of students, creation of circles, circles around us, and utility of circles. So let us go ahead a bit. This we have already talked about, given 4 points, how many circles can be drawn. So there are some problems. I will not be doing these problems here. I will ask Nitish to circulate the problem set via email or if possible now itself, so that you can do these problems later on with yourself. If it was a face-to-face workshop, we would have done it together. We would have utilized the cooperative learning, collaborative learning, and solve them jointly. But now you have to do it only if you want to collaborate with your fellow teachers. You have to call them and say. But I will strongly urge that these problems, take one problem at a time and solve it and put it on WhatsApp. That will be very interesting, very encouraging for me that you are really following what we are trying to tell you, right? So I'm slowly going through some of the problems which are already on my slides, so that later on you can sort of look at them and try to solve. Others will be shared with you by Nitish as a PDF document. So here are some problems. If there was an interactive session face to face, I would have shown you some GeoGebra applets on these also. But when in the video, you can just pause and look at the problem and try to solve them. So as an application, you can try to find out what is the distance of Earth's orbit and what is the light, speed of light, and so on. Problems are there. You can also look at. So let us look at something, a concept called tangents that we learn in geometry of circles. When a line touches a circle only at one point, right? And we have already defined what is a tangent. So this is good for apply and evaluate for tangents, a short kind of video. Tangents around us. You must have seen in mechanical devices a belt moving something, rotating something. So the belt is tangent to the object. Here when you throw it, the discus goes at a tangent to the arm circle created by the arm. How the eclipses are formed, lunar eclipse, solar eclipse, and so on. So these are basically tangents that you come across. So let us go ahead a bit. So we have already defined when you prove a line is a tangent to circle if it is perpendicular to the radius drawn to the point. So these are the theorems that you prove about tangents. I'm just quickly going through them. Here is something interesting. So let us see what it is. I'm trying to give you some inputs on apply and evaluate. So here is a question, just to bring your attention. Most of the video was about trains taking turns on curved tracks, mostly on hilly stations and so on. So how are those rail tracks designed? How much turn is required? How much they should turn around? This is a very is a bit not very tough job, but it is a job for civil engineers and engineers working in the railways when they want to lay down a track on a hill station or a hilly area, and when you have to turn, you have to keep into mind the various things. One, for example, how long the train is going to be, how much turn it requires, right? There can't be very sharp turns because the train may not be able to turn, and we can't have a very long turn also because that much space may not be available. So how do you design the turn? Of course, the turn is a part of a circle, a circular arc, which is the turning of the track. How does that railway track joins that arc? How it leaves that arc? So these are the various questions, and the important thing is in this, what is that length of that arc and how does it join that arc. So this is what it looks like, that if this is the turn that we want, this is a turn, railway track, right? And this is the center of that circle, the track that we want. So this railway track which is coming should join this in a tangential way, so that there is no jerk in turning. So this line is a tangent, and when it is leaving, it should also leave in a tangent. That's why these angles are 90 degrees. Now the question is, what is this angle A to AOB? How much angle is minimum required? So railways have gone through this statistical data, and it doesn't have gone somewhere else. I'll have to go back, and I think the link is not proper, so let me not bother much about it. We were already at, I clicked the wrong thing. I think I have shown you most of it anyway. So here is thing, edit, view, full screen. It's okay for everybody, I hope so. So here is, this is what I have done, it is in GeoGebra, the possible design. And so this angle AOB is a minimum angle. I think I'm not very sure about it, I don't remember it. It is 75 degrees. So this arc EOB should have at least 75 degrees. It could be bigger if the space is available, but it should not be shorter, otherwise it will be difficult for the trains to turn. So this is one of the applications of tangents in designing rail tracks. Okay. Here is another application of circles and tangents. So angle of an angle cannot be trisected mathematically. Given an angle, you cannot trisect it using a straight edge and compass. It is known that you can't do it. But geometrically, one can do it. Of course, you will not get exactly, but there will be approximations which are not very bad. So it was proved by Pierre Wenzel that it is impossible to solve this problem mathematically, because it leads to a cubic, and so solving those cubics. But geometrically, we can do it. And there is a tool which was used long back. I don't think it exists now. It is called tomahawk. So this is a tool. This is a semicircle part of it, and there is a blade attached to it. This is a blade that is semicircle, and there is a handle. This part of the straight line is divided into three parts. The first part, the second part, the third part. These are three equal parts, and this is a semicircle, and this is a tangent to that semicircle. So this is an instrument called tomahawk, okay, which was used long back. So this is what I have described in the words, that is what it looks like. So how it is used in trisecting an angle, so let us just look at it. So if an angle is to be trisected, ABC is an angle which you want to trisect, then what you do, you put that tomahawk, right, that handle, okay, goes at the base of the angle ABC, okay, and if you join that center of the semicircle which is marked on the tomahawk vertically, then one angle is ABE, other is EBF, and the third is EBC. So those are the three angles which are equal, and that can be proved very easily using elementary geometry, that this will be equal. Okay, so this is how this tomahawk is used to trisect an angle into three parts. Okay, that is the position. ABC is to be trisected, then the circular part is kept on this arm of the angle AB, such that the vertical handle passes through B, and that's all is required. And you mark the center here, and that gives you the three angles. So that is another tool which was designed long back and used for trisecting an angle. So here is another one called Arbilos. Arbilos is a tool. I don't know whether modern cobblers use this or not. This is the shape of. It is a kind of a knife. This edge is sharp. Okay, it is a part of a circle. Here is another circle here and another circle here. So there are 3 circles, and is a part of that. So this is what the Arbilos looks like. Okay, so this is a half of that. So this is one big circle, and that is, here is the handle. Okay, below it. So there are 3 touching circles which give you the construction of that Arbilos, and it is a tool which is used by the various. It was used by cobblers earlier for various things. So I think Google is the best way to look at this word Arbilos and its applications, history, and so on. Right. So this is what Arbilos looks like. You can. I tried to construct it in GeoGebra. And let me see whether I can. My construction. Yes, it is here. So this is Arbilos. So construction of this Arbilos in GeoGebra itself helps you to learn many things. You have to take a bigger circle. You have to, inside you have to put 2 semicircles which are touching each other, and the third circle which is touching these 2. So construction of this circle is not that simple in GeoGebra. I downloaded it from org GeoGebra. It was available, so instead of spending time on it, I downloaded it and I'm showing you. But I tried to spend some time in constructing it. Please stop your mic. Don't let your mic go. Okay. So those who are experts in GeoGebra try to construct. Please shut your mic. Please shut your mic. Okay, so let us go ahead. So this is, I think here is probably a video. Probably let me show you a part of it, which shows you how circles and arcs are used in architecture. So you see the circles, arcs. In Europe, you will find this architecture very common in old buildings called Gothic architecture. So this is useful in architecture. You can find YouTube videos on it. Okay. Here are some problems which we are not dealing. So I'll just go through quickly these problems. You can pause later on and video and try to solve. And we are also going to circulate PDF for the same. There are various problems on circles, touching circles, and calculations and such things. They're all interesting problems. So those you should try to solve them. And so here is something on rainbows. So rainbows are also constructed or they get made when there is a total internal reflection from raindrops, and all the rainbows are parts of circles. So let me skip that. So we do arcs and angles and such things. So let me skip these things. These all define and prove. And there are problems on that. So I'm just clicking them so that they get recorded, and you can try to solve them using later on. There are many. This is something on inscribed angles, a video on inscribed angles, how inscribed angles are useful in life. These are problems, and you'll get hard copy for the problems. I just want to close this with one illustration of. So this is another interesting thing in the cameras. When you do what is called taking photos, when you zoom and zoom in, zoom out kind of thing, you are increasing the angles of view. Okay, so circles and angles, arc angles are important in that. So this is problems on that. Now mathematics is entering into sports. People analyze training of sports personnel, sportsmen. So at what point you should shoot so that in football, so that you will go into the goal, and that is analysis of that kind of a thing is again depends upon knowing mathematics, circles, angles, and so on, arc angles. Okay, so here is something that I finally wanted to show you and then conclude. We all know that there was a movie called Titanic, which is based on an actual incident when a ship sank on its first voyage. It hit an obstacle on the way, and so like a ship was coming and it hit and it got drowned. It did not know that how to avoid that obstacle. So here is a small movie, and there is a problem based on that. So that says, how did Titanic sink? So this is an important question in ship navigation. How does ships avoid hitting rocks? And for every danger zone, there is a danger angle which they should avoid, which they should maintain to avoid hazardous regions. What is that danger angle? How it is calculated? That is a part of the problem. Let us say there is an obstacle. So there is an obstacle at a point C in the ship. To warn the ship, 2 lighthouses are put on the shore at points A and B. Sometimes it may not be possible to do this kind of a thing, but let us assume that the obstacle is not very far away from the coast, and there are places where you can put these lighthouses put on the shore A and B, then that angle between ACB is called the danger angle, which they should avoid. So that danger angle is known and can be calculated by the ships at a particular. So this is what it looks like. So this is the rock, which is, and this is one lighthouse A and another lighthouse B. So this angle ACB is the angle that the ship should avoid. So the ship should either go on this side or on this side. It should not be coming in between. Otherwise, there will be a danger of hitting. So if the ship enters this side, inside this, chances of hitting it are there, hitting the rock. So this danger angle for every obstacle is sort of plotted and known. So what is a safe angle for the ship? At what angle they should go so that they avoid this. So given the knowledge about ACB, what is that angle ASB? How does one calculate that? So to calculation of that is not very difficult. There is, if this angle C is is given 110 MAB, so measure of this arc. Okay, if this is 110, we want to find first. I want to take a point on the circle. What is a circle? That is a circle which is including the point C, and D is a point on the circumference. So we first calculate ADB and then calculate this other angle. Okay, so to do that, so here is the problem, that how does these calculations are done so that you get a safe angle. So S is this angle which is a safe angle. So to do that, let us just observe that this is A and that is B. So that is obstacle. This is the point S, that is the ship. That is angle S we want to calculate. So by the formula for if D is a point on the circumference, then this is half of AB, because AB is a circle with center. This angle is 110 given, so this angle will be half of that, right? Whatever be the circle center, this is the angle on the circumference, right? D, an angle at the center, so that is half of AB. So this is half of the center, so that is 55, right? So then we use our theorem, what is called the secant angle theorem, that ASB is half the measure of angle AB minus half the measure of the angle CD, so less than 55. So S is the danger angle, which should be at least 55. So that 55 is the angle for the same. So with that inputs, let us stop for this session. So what we have tried to do is give you some inputs on observe and explore about the definition of a circle given by Apollonius. We have tried to give you inputs for observe and explore, for tangents, and inputs for define and prove. You will bring in coordinate geometry into saying interior, exterior of an angle. We have given you some inputs for apply and evaluate. Of course, a problem set will be coming to you, but we have tried to give you some interesting applications of this apply and evaluate. So with that, we come to the end of the presentation. I don't think it's possible to take question answers on this. I think it's difficult to take questions. 95 questions already and 84 participants which are there. Yes. So let me thank you all for coming for the session. Thank you, thank you, Professor Santosh, Narpure, Nitish, and Mahesh for helping in organize this session. Thank you very much. And comfortable stay at your home till we are allowed to work.